Welcome to video 14.4 in our first Principles of Astrophotography series. In this video, we discuss stacking.
This video is based on section 14.4 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 151, probably my favorite, stacking. Stacking is the process of averaging exposures to increase the signal-to-noise ratio.
Stacking is where you say, I'm going to take a 1 minute exposure. And let me say I'm going to do that 10 times. Except for read noise, which we're not really worrying about too much. That's the same as taking one 10-minute exposure.
It's the same amount of light overall. Yeah.
So let's do an example. In Whirlpool Galaxy, we took an image of this a couple of years ago with the Seestar S50. It's a darling little scope, and it's pretty darn amazing, and it has really changed the face of astrophotography.
We wouldn't be here without the Seestar.
No, we wouldn't.
Actually, the cool thing, I loved the Seestar because I didn't have to know anything about the sky. This guy knows everything. I didn't have to know anything. I sat on the ground, and then I hit go, and it goes to the object. And I can watch on the screen as it stacks live, and my picture goes from this blob just every single time. It gets a little better and a little better. Coolest thing.
Yeah. Yeah, it's an amazing scope, and it really has changed the face of the hobby. And now we have the Dwarf series and the Origin, the Celestial Origin, and several others out there that. But when we started off, we didn't really want to think about what in the heck is a guide scope and why would you want one? What camera should I buy? You know, all these things. The Seestar does everything for you. So we have fond feelings for our Seestar S50.
Love it.
Let's pretend that we take a 60-second exposure, 1 minute, of the Whirlpool Galaxy. And in the next slide, I will show you that my estimate of its length and width is about 0.18 degrees by 0.10 degrees. The Seestar pixel size, camera pixel size on that little guy is 2.9 microns, and its focal ratio is 5. The visual magnitude, namely the amount of light that's received in the visual passband of the Whirlpool Galaxy, is 8.4. And you can just look that up in your favorite source. This is a constant we derive in our book. And you plug all those numbers into this formula. This is a formula that we derived in the previous video. And you get a signal-to-noise ratio of 2.1 for a 1 minute exposure. So, and actually, at that time, the Seestar didn't allow 1 minute exposure. So I think it was probably 6 10-second exposures.
Probably.
Or 3 20-second exposures.
Sure.
I don't even remember, and it probably doesn't matter a whole lot. But the thing I'd like to point out in this formula, and what we're going to look at right now, is that variable t right there. So the signal-to-noise ratio will increase with the time spent on the object, but it only increases as the square root of the time. So if you want to double the signal-to-noise ratio, to double it,
which will give you more signal and less noise, right?
More signal relative to the noise, which is what matters. You must quadruple the time.
Stupid squares, square roots.
So if you let, if you put a 4 inside here, and you got 4 times the time, then square root of 4 is 2, and that doubles the signal-to-noise ratio. So in other words, if you want to double the signal-to-noise ratio for this 60-second image, then you're going to have to go to 4 times that amount. So instead of 1 minute, you need 4 minutes. So 4 minutes would double the signal-to-noise ratio from 1 minute to 1 minute. Okay, so let's see what these look like. And the fun thing about this is knowing what the signal-to-noise ratio is, and then looking at the images and seeing if you can tell a difference between images taken with different amounts of exposure time. So this is with the 1 minute and signal to noise ratio of 2.1. And Ren, you can just comment on that.
Unrecognizable. If I looked at that without knowing what it was, I might be able to tell it's the Whirlpool Galaxy.
And we know what it looks like because we just looked at the slides before we started this video. But, you know, there's some spiral arms that come out, and there's a little blobby thing here. But it's pretty hard to tell anything. And the other thing we might point out, this granulation right here is a telltale sign of noise. That's what it looks like in your images. And you'll see it most clearly in regions that aren't receiving very much light. You don't see that granulation here in the bright centers of the galaxies. You see it out in the faint wispies. And honestly, we're kind of faint wispy guys. We love the faint wispies, and we love trying to bring out the details. That's what I think is the most exciting thing about astrophotography. It's trying to capture those little details. Yeah.
It's taking pictures of the dark. You go out in the middle of the darkest time and take pictures of the darkest area.
Yeah,
of the darkest
area. Yeah.
It is the dark.
Okay, so that's what the 1 minute looks like. Here's 4 minutes.
There we go.
And we've doubled the signal to noise ratio. We've quadrupled the time. And you can definitely start to see the structure a lot better. The problem with the previous one, with this 1 minute thing, is we're collecting so few photons. In fact, if the signal to noise ratio is 2.1, then remember the signal to noise ratio is the square root of the signal. Then that means if we want to solve this equation for the signal, then that's the signal to noise ratio squared. So the signal is 2.1 squared, which is around 4, which means that on average, each pixel within this this rectangle, this 0.18 by 0.18, is receiving on average 4 photons.
Yeah.
And so, you know, and some of them out here, I mean, the sort of an average pixel is going to receive around 4, but these out in the fainter regions are going to receive a lot less than 4.
Yeah.
And in here, you're going to receive maybe 8 or 10 or 20, but you're still just not getting very many photons received. So here, the actual signal, which would be the square of that signal to noise ratio, would be around 16. So on average, you're getting about 16 photons per pixel, and you're starting to see some structure. At 42 minutes, so we're multiplying 4 minutes by 10, and we've increased the signal to noise ratio from 4.1 to 13. Now you're starting to see some structure, and because 13 squared is around 169, so you're getting on average 169 photons per pixel, and you're starting to see the structure. But
well, more than the structure, you're starting to get the connections of the wispy.
Yeah, we got a little connection here. But at the same time, the fainter regions, I mean, this bright region right here doesn't look noisy.
No.
But if you look out here in the fainter regions, it looks pretty noisy.
It's the same thing we're getting, yeah, for sure.
So this is 512 minutes. We've multiplied the time by a factor of 10 now. And clearly, I think we did some processing on this one too.
Oh, we did our best.
Yeah, we did our best. It's not the best Whirlpool you ever saw, but it's not bad for a Seestar S50, honestly. And we're pretty proud of this image. We're starting to see some of the dust lanes that you can barely get an idea. There might have been a dust lane there, and maybe here, but now definitely you're seeing some of these, and we saw that connection between the main galaxy and its satellite galaxy. The fun thing about astrophotography is that the more time you spend on an object, the more detail you're going to see in that object. And so, I mean, when we started off, we just wanted to shoot everything, and we spent an hour or two on each object and shot a whole bunch of stuff. But now we'll spend several nights on each object, and
we'll
then
spend a month on an object.
Yeah, and waiting for
Good
clear
skies,
nights
yeah.
and moonless skies. And
But when you look on Astrobin and you see amazing photos, it helps you appreciate those people put in so much time just collecting the data, just getting those 20, 30, 40, 150 hours, getting all of that data just so they could get good signal to noise. This was the reason, so they could get all that signal and smash the noise.
And I really think that there are two things that make this hobby rewarding and satisfying. I don't know if it's very fun kneeling in 2 feet of snow out in Treasureton, Idaho, which we have done, trying to get the scope polar aligned or whatever. But it's satisfying after you've put the time and effort into taking the images, then you put the time and effort into processing the images, then you have something you can really be proud of.
Yeah.
Thanks for watching.
And we'll see you next time.